Hello, greetings. I'm here to present my findings on the data communications coursework. My name is Okoth Vien Trevor, and these are my findings. So we're going to start with the frequency division multiplexing. This is a technique by which the total bandwidth available in a communication medium is divided into a series of non-overlapping frequency bands, each of which is used to carry a separate signal. So, for signals to be transmitted by frequency division multiplexing, the combined bandwidth of the signals should not be greater than the bandwidth of the link transmitting the signals. Okay? So, these signals all have similar frequencies, and when they arrive, they are sent to the multiplexer, which combines these independent signals from the input lines, combines them into one band, and this band is sent over the transmission link to the demultiplexer. On reaching the demultiplexer, these signals are broken down into their individual signals. They are decomposed, they are broken down into individual signals and sent to their transmission. So while these bands are being transmitted, while the signals are being transmitted, we have what you call guard bands, of which guard bands are strips of unused bandwidth that are used to prevent these signals from overlapping and interfering with each other. Then we move to wavelength division multiplexing. Now this one is conceptually the same as frequency division multiplexing. They share the same concept, whereby signals are put into a multiplexer, then they are combined into one band, which is sent over the data signal, over the data medium, the transmission medium, and when they are sent, on reaching the demultiplexer, they are also decomposed into their individual signals. The only difference being that in wavelength division multiplexing, we transport signals over optical fiber cables, and these optical fiber cables transmit optical signals. So these signals, to be transmitted over the medium, they should have similar wavelengths. So when they are put into the multiplexer, they're transmitted, then separated when they reach the demultiplexer to the individual signals. So the optical fiber data rate is higher than that of the metallic transmission cable, which makes wavelength division multiplexing faster than frequency division multiplexing. So we go to synchronous time division multiplexing. In time division multiplexing, multiple transmissions can occupy a single link by subdividing them and interleaving the portions. In time division multiplexing, time frames are allocated to each transmission source, whereby that slot is meant solely for transmitting data from that specific source. Now, in synchronous time division multiplexing, each source has a slot in the time frame, and that slot is there even if the source is transmitting signal or not. That's the difference. That's the feature of synchronous time division multiplexing. And here, multiple transmissions can occupy a single link by subdividing them and interleaving the portions. So here, the time frames are divided into slots which are given to each signal source. That is synchronous time division multiplexing. So if we have 4 inputs, the frame will have 4 slots each for each data source. Then we go to interleaving. So the time division multiplexing can be visualized as 2 fast rotating switches, one on the multiplexing side and one on the demultiplexing side. The switches are synchronized and rotate at the same speed but in opposite directions. So on the multiplexing side, as the switch opens in front of a connection, that connection has the opportunity to send a unit into the path. So we can see that this first frame, this first rotating wheel, as it's rotating, data bits are sent into the rotating wheel. Then when it rotates and there's an open path, the data signal is sent through the transmission medium. Now on the other end, we have the demultiplexer, which also rotates in an opposite direction. So when it opens up in front of the connection, that connection has the opportunity to receive a unit from the path, and that's how interleaving is achieved using time division multiplexing. That's the diagram. It also has frames because the signals are divided into frames with time slots, then they are demultiplexed when there is a demultiplexer and broken down into their individual signals. Frequency hopping spread spectrum. So in spread spectrum, we combine signals from different sources to fit into a larger bandwidth, but our goals are to prevent eavesdropping and jamming. So frequency hopping spread spectrum is a method of transmitting radio signals by rapidly changing the carrier frequency among many distinct frequencies occupying a large spectral band. The changes are controlled by a code known to both the transmitter and the receiver. How does it work? So in frequency hopping, a pseudo-random code generator creates a k-bit pattern for every hopping period. We can see that on the left side you have a pseudo-random code generator, and this generates a k-bit pattern for every hopping period. So the frequency table, this yellow frequency table, it uses the pattern to find the frequency to be used for this hopping period and passes it on to the frequency synthesizer. So the frequency synthesizer creates a carrier signal of that frequency, and the source signal modulates the carrier signal. The frequency of the carrier is periodically modified following a specific sequence of requests. So in frequency hopping spread spectrum, the spreading code is this list of frequencies to be used for the carrier signal. So from this diagram shows us how the k-bit patterns generated by the pseudo-random code generator are converted into the frequency. The k-bit patterns are sent to the frequency table using the k-bit patterns, which are transmitted into the frequency that is output. And that ends the part 1 of the session. So in part 2, we are told to explain how the multi-carrier modulation scheme, known as the FDM, works, what is meant by inter-symbol interference, and differentiating between uniform and non-uniform quantization. So in multi-carrier modulation scheme, a multi-carrier, it's a form of signal waveform that uses multiple normally closed spaced carriers in a block to carry information. So in this multi-carrier modulation, we use the principle of transmitting data by dividing the stream into several bit streams, each of which has a lower data rate. Okay, so multi-carrier modulation has several advantages, including resilience to interference, resilience to narrow band fading, and multipath effects. And as a result, multi-carrier modulation techniques are widely used for data transmission, as it is able to provide an effective signal waveform which is spectrally efficient and resilient to the real world. Okay, so here is an illustration of the multi-carrier modulation. It shows the different carriers which are combined and put into one form. Yeah. So this explains how it works. It divides the data streams into a number of lower data rate data streams, each of which has a lower data rate. Then when the overall transmission is received, the receiver has to reassemble the overall data streams from those received on the individual carriers. So it is possible to use a variety of different techniques for multi-carrier transmissions. Each form of MCM has its own advantages and can be used in different applications. Sorry for the mistake there. It can be used. Yeah. So we go to inter-symbol interference. This is a form of distortion of a signal in which one symbol interferes with subsequent symbols. In inter-symbol interference, errors are introduced into the receiver output, and this is caused by multipath propagation and band-limited channels. So here we explain the two causes of the inter-symbol interference, which are multipath propagation and band-limited channels. So in multipath propagation, here a wireless signal from a transmitter reach the receiver via multiple paths caused by reflection, refraction, and atmospheric effects that affect the signal as it's being transported. So because of the many paths of different lengths, the different versions of the signal arrive at the receiver at different times. Okay, and that leads to inter-symbol interference. Then band-limited channels. These are channels where the frequency response is 0. above a certain frequency, which is called a cutoff frequency. So passing a signal through a channel results into the removal of frequency components above this cutoff frequency. In addition, components of the frequency below the cutoff frequency may also be attenuated by the channel, or they interfere with the frequency. Uniform and non-uniform quantization. So quantization is the process of mapping continuous infinite values onto a smaller set of discrete finite values. So in uniform quantization, here the quantization levels are they're uniformly spaced, while in non-uniform quantization they are unequal and the relation between them is logarithmic. Uniform quantization is more prone to quantization errors, but non-uniform quantization reduces the quantization error or is more stable compared to the uniform quantization. We go to part 3 where we talk about satellites. A satellite is an artificial body placed in an orbit around the Earth or another planet in order to collect information or for communication. So there are 3 categories of satellites used in communication systems, and these are located based on their, they're classified according to their location on the orbits. They are divided into the low Earth orbit, middle Earth orbit, and the geostationary Earth orbit. Okay. Now the geostationary Earth orbit is located far away from the Earth, over 35,000 kilometers. Then we have the middle Earth orbit, which is located in between the Van Allen belts, and this is normally between 5 to 15 kilometers from Earth. And then the closest to Earth is the low Earth orbit, and these are the 3 different types of satellites that we use in data communication. So here we talk a lot more about the low Earth orbits, which are located between 500 to 2,000 kilometers above the surface. Their low altitude means that they are visible from within a small area beneath a satellite as it passes overhead. So because they change positions relative to the ground quickly, a large number of satellites are needed to avoid breaking the connectivity. Then we have some few uses there about the low Earth orbit, where there is low data rate messaging and broadband internet access. So in middle Earth orbit, these satellites have an orbit of around 18,000 kilometers above the Earth's surface, with a rotation period of 6 to 8 hours. They are positioned between 2 Van Allen belts, as I said earlier. Then a satellite cannot exist inside the Van Allen belts, as it would be destroyed by the energetic charged particles that are found inside the Van Allen belts. Then lastly, we have the geostationary Earth orbit. Here the satellites are farthest away from the Earth that they appear to be stationary when viewed from Earth. That is, they are over 35 or 36,000 kilometers above the Earth's surface. So because they rotate at a constant speed, they are constrained to rotate over the equator. This also reduces on cost for expensive equipment to track the satellite's motion. So one of the uses of the geostationary Earth orbit, they're used to monitor the weather over various areas. Yeah, and that ends my presentation. Thank you.